All right, so covalent bonds. All right. Covalent bonds. We're starting chapter 4. What are covalent bonds? Remember, co means sharing, valent means we're talking about valence electrons. A covalent bond is when you bring two atoms together and they share valence electrons. Okay. Let's get rid of that. Didn't realize that was still up. Two atoms come together. Each one donates a single electron, and you get a bond with two electrons in it. So you have atom A, atom B. Each one donates a single electron, and you have a bond between them. And it looks surprisingly cute. Okay, so a bond has two electrons in it. You can get more than one bond between atoms. You can get a double bond with 4 electrons. You can get a triple bond with 6 electrons. And that's it. You can't get any more than that. It gets too crowded, and they can't really bend that way. There's just not enough room for them to get more electrons in there. So a single bond is strong, a double bond is stronger, a triple bond is stronger still. Now, I want to go ahead and stress a double bond is not twice as strong as a single bond. A triple bond is not 3 times as strong as a double bond or as a single bond. They are stronger, they're just not 2 and 3 times stronger. It's slightly more complex than that. A stronger bond is also a shorter bond. Okay, again, a single bond isn't exactly long, but double bonds are shorter and triple bonds are shorter still. We often model bonds as springs that are holding the two atoms together. So you have your two atoms and the bond is a spring that holds them together. They are able to bounce around, they can wiggle, but ultimately they stay together. And the stronger the spring, the more closely they are held together. So the stronger the bond, the shorter the bond. So a triple bond is going to be the shortest. A single bond is going to be the longest. And that is ultimately what gives us the differences between our different kinds of compounds here. We have an ionic compounds and we have covalent compounds. So an ionic compound is a network. It's not a single individual molecule the way a covalent compound is. So remember, when we're looking at an ionic compound, you get these networks of positive ions, where each positive ion is completely surrounded by negative ions. Each negative ion is completely surrounded by positive ions. And they're being held together by their electrostatic forces, okay, such that every negative ion puts out a negative electric field in all directions simultaneously. Every positive ion puts out a positive electric field in all directions simultaneously. So the forces that are holding this crystal structure together for this salt, they are non-directional. They are universal. Okay? They're everywhere, sort of all at once. Contrast that with your covalent compound. Okay? Covalent compound is made of these individual molecules, where an ionic compound, if this was sodium chloride, that chemical formula only represents the ratio between sodium and chlorine. On the other hand, if you have CO2, this actually represents a molecule where you have a single carbon atom bound to 2 oxygen atoms. And that's it. It is actually talking about this specific unit of matter, okay, a single individual molecule. So ionic compounds, this is a ratio. Covalent compound, this is an actual molecule. Other things we see, ionic compounds have ions. Covalent compounds don't have ions in them. They can have, they can be ions. They're not made of ions. Okay? And that's what gives us the different properties of. So when I say local directional bonds, I'm saying that these bonds are entirely located in between these two atoms. Very directional, as in they hold these two atoms and only these two atoms together. Whereas the forces for ionic compounds, they're going out in all directions, regardless. Okay? So they are not really localized. It's the entire structure is being held together rather than individual atoms. So that's what gives us these properties. Salts are brittle, covalent compounds are soft. Okay? If you were to, hit this with a hammer, you shift it very slightly, then instead of having negative next to positive, you'd have negative next to negative. And then the very same forces that are holding it together in this nice pretty structure would, boom, force it apart. So they shatter. The forces that hold covalent compounds together are very, very strong, but they're only located inside the molecule. The forces between molecules are incredibly weak. Okay? So if you have two CO2 molecules, the bonds inside here, between the carbon atoms and the oxygen atoms, those are really, really strong. But the forces in between the two guys, they're very, very weak. They don't interact anywhere near as strongly. It's an incredibly weak interaction. So it's really easy to separate these two individual molecules. And that's what also gives us the melting and boiling point differences for ionic and covalent compounds. Ionic compounds have very high melting and boiling points. Covalent compounds have very low melting and boiling points. When you heat up a liquid, or when you heat up anything, what you're doing is you're making the particles move faster. Okay, particles are always in motion, constantly, vibrating, rotating, wiggling around. And as they get hotter, as they get warmer, the temperature increases. They move faster and faster. And eventually they move fast enough that they can break the forces holding them into the solid, and it melts into a liquid. They move faster still, they can break the forces holding them into a liquid, and they boil into a gas. So when you're increasing the temperature of an ionic compound, in order to melt it, you have to separate all of these forces all at once. You have to overcome the bond strength holding the ionic compound together, and that is really, really hard. So you have to raise the temperature incredibly high. Okay, so whereas covalent compounds, these interactions between the molecules are what you have to overcome. And these interactions between the molecules are very, very weak. So you don't have to raise the temperature very high in order to melt or boil a covalent compound. Thus, ionic compounds have temperatures in the hundreds or thousands of degrees Kelvin, whereas covalent compounds have temperatures in the dozens of degrees Kelvin, or up to hundreds for some of the bigger molecules. Finally, ionic compounds are conductive. They conduct electricity as a liquid or when you dissolve them in water. Remember, electrical conduction is about the movement of charged particles. Ionic compounds have those charged particles. They're ions. Okay, so you melt it or you make it a liquid, and suddenly these ions are free to move. You apply an electric field across the liquid. The negative ions move one way, the positive ions move the other way. Conduction. Okay. The same thing happens if you dissolve it in water. Okay, the ions are now free to move, so they can conduct electricity. These guys, solid, liquid, gas, doesn't really matter. Their electrons are all locked down. They're not going anywhere. So covalent compounds are all insulators and not conductors. All right, that does it for this particular set of slides. This is very short. These 3 lectures I'm going through today will all be very short like this. Our intro to Chapter 4 is not going to take very long, and now Sasha is over here. He's exploring the new lamp I put up. It's hot. He'll learn that all on his own. I hope it doesn't hurt him too much to learn that. All right, so that is it for this particular lecture. I see no questions in the chat, so I'm going to go ahead and end this particular stream. I will see you again in about 5 minutes.